PhD student at the University of Canterbury, and today I'll be sharing what we've learned so far from the rich Colossus UVan dataset. Hopefully with this talk I'll demonstrate that the near UVs can reveal some unique surface compositions. So, quick overview of Colossus, or the colors of the Outer Solar System Origins survey. Colossus is a survey of TNOs that covers the near UV to near IR with broadband photometry. So on Monday we heard all the GWSC spectra talks, which is here, the wavelength regions, but I'm bringing you all down to the shorter wavelengths now. So the main Colossus survey was done in the GRZ-J bands on Gemini North, and the next talk, or Buchanan, will talk about dynamical implications of these colors. But for this talk, I will be talking about the UVan, which was taken simultaneously with the data taken on Gemini North, but UVan was done on CHT. So the discovery survey for Colossus and this data set is Colossus, and we heard about that earlier this week as well. And this survey is distinctive for having well-characterized biases. And our UVan survey is the brightest limited sample of the Colossus discoveries. So here we can look at how the targets of this survey break down by dynamical class. So here are the UVan targets, and here are the OSIS dynamical classes. They seem pretty similar, which is reassuring. So for our UVan data, they're kind of split into two. So the biggest chunk of it is actually non-detections. So these are like R magnitude around 23.5 to 24.5 objects. So in the UVan, they're even fainter. But we can still extract useful information from them. We can get upper limits on these objects. This is still a work in progress, but we've done about 40 out of like around 120, and the upper limit so far range from like 26 to 27.5 in UMags. Yeah, so the other portion of this data set is the simultaneous TNO colors. So there are 52 of them with measured U-R colors, and these objects have simultaneous GRZ-J photometry from Gemini North. And so bringing it back to what Colossus in general has found. So two main things. One, the majority of TNOs in the optical near IR space follow something called the Rembrandt curve, which is a line of constant spectral slope. So here, G-R-J, so optical near IR space, we see the Rembrandt curve, the solid line. The other thing is that TNOs that can be split into two surface classes. So in Fraser et al. 2023, we find that you can split these objects into two classes with this orange dashed line, which is parallel to the Rembrandt curve. And so the objects above this dashed line are the bright IR objects, below the faint IR objects, and the co-classicals largely fall in the faint IR class. Okay, so how does this all map onto optical near UV space? So, okay, we have our Rembrandt curve, and just to hammer it home, Rembrandt curve, objects on the Rembrandt curve, flat spectra, or some sort of gradient. Objects above the Rembrandt curve is a UV drop, so either some sort of gradient change or like a dip in the reflectance. Objects below the Rembrandt curve, a UV axis. So again, some sort of slope change or some sort of UV bump. And okay, so we plot the co-classicals on here. Looks like it's on the Rembrandt curve. We plot all the dynamically excited objects. Also kind of looks like on the Rembrandt curve. So by eye, it seems like they all kind of fit together. But I wanted to approach this a bit more quantitatively. So for the sample, the dynamical classes kind of behave differently in the color space. And how well does this rendering curve actually fit this data? So I use this approach that I'm calling the center mass statistic, which is basically just a bunch of simulated averages to find where each dynamical class lies in the color space. So let's take, for instance, the whole classicals. Each object's true color can be described by distribution, right? That's centered around its measured color, and its spread is described by its photometric uncertainty. So you can draw a clone of this object from this distribution, like so. And then you can repeat this for all the objects. And then you can take an average of this, just a simple average of these colors, and then you have this, I'm calling a center mass, and then you just repeat it many times. And so all these little faint dots is the many center mass is being calculated over time. And the density of these spots represents where the overall probability of the true center mass these objects lie on this color space. Okay, and I plotted an ellipse here to show the lightweight region of where the center mass would be. So center of that ellipse is the center of all these center masses, and the shape of the ellipse is based on the spread of these center masses. And then we can repeat this for all the dynamical classes. And then it looks like there's some sort of trend, right? Then you put the rendering curve on there, and then it seems like, okay, the rendering curve goes through the whole classicals, but for the dynamically excited objects, they're all below the rendering curve. Sure, they kind of like, the rendering curve goes through something, but for example, like the resonant objects, that center mass is definitely below the rendering curve. Not by a lot, but still, far enough away. And so, okay, so for this, I wanted to apply this method to something more familiar, because the event is a newer data set. So something more familiar is the optical near hour data. And so I did the same thing on there, and okay, it still seems like all these center masses are below the rendering curve. But it's strange, but I don't think it's actually that strange. So if we recall back to that Fraser-Hall plot, the idea of having two surface classes is not incongruent with having all these identical classes fall below the rendering curve. Because while, yes, the co-classicals, the faint IR class, definitively below the rendering curve, the bright IR classes, the bright IR class, just needs to fall above this orange dashed line. So it just needs to be above that demarcation line. So essentially we're seeing something similar here. It's just more explicit that objects lie below the rendering curve. So, okay. So back to near UV optical space. We see that, okay, yes, for pi, with this center mass approach, and also just by eye, the majority of objects are UV blue. So anything UV red is unique, and especially that one object I narrowed on there is pretty UV red compared to everything else. Our main context for something like this is the only known TMO that has a definite UV drop, which is this object called EW95. This object was found to have a C-type asteroid light spectrum. So it has a near UV drop, and then this broad absorption feature in the 0.7 micron region. And these two things are associated with having hydrated silicates on its surface. So, so that's having hydrated silicates is a characteristic of C-types. And so we wanted to investigate if we were seeing a second EW95 with this object. So we got Gemini spectroscopy on it. Okay, so we're still working out the kinks on the reduction and analysis of the spectrum. This is a ground-based telescope, so these aren't nice spectrum like the WST ones. But this preliminary spectrum, we seem to see see that there's like a slight curvature in the spectrum. It could be that broad absorption that I was describing earlier, maybe, but so maybe that hydrated silicates, or it's just something else, you don't know. And also this dip is pretty small, so this curvature is pretty small, so definitely we need to do more work to characterize this and to see if it's actually real. But we also definitely see a very red slope in the spectrum, so like much redder than a C-type asteroid, and in fact, much redder than an E-type asteroid, which is the reddest asteroids we have. And so it just behaves more like a red TNO. So our TNOs are the reddest class of TNOs, and so yeah, the slope is congruent with our TNOs. So if we believe both features, then it's pretty weird because we have this TNO-like slope, but then asteroid-like feature. So this object could be interesting. So to conclude it all, I guess the bending curve doesn't seem to be the complete story for TNOs in this region, and this isn't, I wouldn't say this is like a novel thing. The bending curve is definitely just a theoretical model where you assume TNOs just have a flat slope. But what we seem to see is that TNOs are systematically offset from the bending curve somehow. That could be interesting surface characteristics. That is the reason why we see these offsets on like a population level. Hopefully we can learn more from these spectra that's all coming out and can extrapolate this idea to colors, which have more data for more objects. And in the context of near UV, where those things have a UV access, we don't really know what's happening because near UV just has very little data in general. One possible context for this is looking at Trojans. So Wang et al. 2019 found that some Trojans have shallower UV slopes, and a recent paper, and Phoenix et al. 2024 found that some Jupiter Trojans have a UV bump. So perhaps we're seeing these features, one or both, in the TNOs as well. Perhaps it is a continuum, I don't know. So just something to look into further. So we also identified this BD faint object that has this possible hydration, but very red slope, again, if both features are to be believed. And so obviously this brings questions about what could be causing it. We know in TNOs, red slopes are because of complex organics, but can you have hydration absorption with these complex organics? Because usually their complex organics are like very dominant in the spectrum. So, or it's just something else at work. And overall, hopefully I've demonstrated that near UV is interesting and that we should be all excited about the UV data that LSST will bring us. Even though all the survey simulation talks the other day just showed us that detection is terrible in the UVAN, it will still be an order of magnitude at least more than the data we currently have. So that would be very exciting. Thank you.
Great talk. So have you checked if your U-band outliers are also outliers in J-band, or in other words, have you done U minus J versus G minus R?
It doesn't seem like, so for example, that UV faint object isn't an outlier in the optic area. So yeah, it didn't seem like it was correlated.
Can you go back to the plot of your colors to look out the outlier for a second, and then I'll ask you to go in a second. So the error bars are so quite big.
Yes.
Could it just be that it's the uncertainty because it's so faint, or for whatever reason, so it is actually consistent? Because I guess, I don't know if you have a preliminary estimate from your spectrum of how close your U-band color would be.
Yeah, so
if you go to the spectrum, it didn't look like it was a cliff.
So
I was wondering if you could comment on that.
Oh, yeah. So
And the spectrum here looks, or it gets very, I guess, big error bar. So I was wondering if you can comment
yeah, so
if this is just a big error bar.
yeah, so for sure the error bars are huge, but I wouldn't expect near UV drop in just based on the spectrum because there was a blocking filter that was on Gemini for these observations, so we won't actually see any of the band drop in this spectra. So yeah, so I guess, but when I was planning this observation, I prioritized getting the points of micron feature over trying to get the U-band drop because that was more characteristic of trying to get the Sylvia feature.
Hello, did you check if your target was observed by James Webb?
Pardon, sorry.
If this target was observed by the James Webb?
Oh, no, this target was not. But I mean, it would be interesting. So I guess it would be interesting to see the EW95 spectrum, which I know it has been observed, and try to correlate that with this object. So yeah.
So can you go back to the center of mass?
Yes.
So is there a statistical difference in color among different population? I mean, different Hall population, like detached, the Hall classicals, and because they were all thought to dynamically form from the same population.
Place. Yeah. Yeah. So I guess that is something I'm unsure. I feel like that needs more statistical analysis. Because I think this was more trying to get to grips on like how well does the data fit the Redman curve. I would say, yeah, but that would be interesting.
Kind of go about this is a really cool talk. The spectrum of that one object, in GRJ, do you know what the surface classification was of this guy? If it was bright or green.
Oh,
We can talk later.
yeah, I definitely have this in my mind like yesterday. Now I'm thinking, I'm sorry.
It was bright. It was bright.
Oh, it was right? Okay, cool.
Questions? Okay, I think we can go lunch.